Okay, folks, the next one is going to be atomic structure. So, finally. First thing, one of the things we need to understand is how electricity interacts with our atoms and what do we mean. So, first off, one of the things you should understand is all electricity is moving electrons. So, literally, electricity is just electrons in motion. So an electrolyte, this is going to be a compound that conducts electricity when it is molten or dissolves in water. And so one of the things you should know to understand electrolyte properly is that water is actually not very conductive. It's quite resistant to the conduction of electricity, meaning that if you had a pure water and you were standing in pure water, then a lightning bolt came down, you would actually not get very electrocuted. You will not have a lot of electricity pass through you. If you stick wires into pure water, it will actually not conduct electricity well. Now, why water normally does conduct electricity well is it is not pure. It is ions dissolved in it. Specifically, it has electrolytes dissolved in it, like table salt, NaCl, and various different magnesium, calcium chloride, that sort of things. And these ions are what cause the electricity to be conducted through water relatively well. Of course, not as well as a normal wire, but pretty well overall. And again, those are because those are electrolytes, and they are then dissolved in water, making it conductive. Now, electrodes, these are carbon rods or metallic strips that carry electrical current. And so electrodes, you probably have heard of this term and seen electrodes before. The little prongs on a taser, those are electrodes. Okay, this is probably the most common electrode you've seen. The little prongs you see on batteries are also electrodes, by the way. So, in electrolysis, you have two things. These are your electrodes. One is always the anode, and one is always the cathode. And so the anode is the positive electrode. The cathode is going to be your negative electrode. One of the ways you can help yourself remember this is this negative electrode has positive things attracted to it. And so, much like a cat has many positive things attracted to it. Like, for example, the most popular Facebook page for almost 30 years now is a Facebook page for cats. So that's cathode. Positive things are attracted to them. Now, anodes have negative things attracted to them. That's because the anode itself is positive, and so the anode has negative things attracted to it. Much like most people like the taste of sugar, but it attracts ants, right? All right. Ion. An ion is an atom or group of atoms that have a charge. So an ion will have a positive or negative charge. And this is because it has gained or lost an electron, one or more electrons. An anion will be a negatively charged ion. One of the ways you can help yourself remember an is negative, and that is that ants are negative. If you have ants at your picnic or ants in your house, that's a negative thing. So anions are negative ions. A cation is a positive ion, and so cats are positive, cations are positive. Now, this right here was the mid-1800 Crookes tube. This actually showed the relationships between electrons, electricity, and their magnetism. It's a negatively charged. So what this is this is actually the same thing as a phototube. It's very similar to it. And if you've ever heard of like the boob tube, which was the TVs back in the day, or seen one of those really big old TVs, remember the ones that were really thick and really heavy? If you dropped them, they made this really loud explosion sound. Anyways, those were actually cathode ray tubes. That's what those were made out of. The only difference being that this coating right here that shows when an electron hits it, this was at the end here, and it was elongated like this. so that the electrons that hit it would cause flashes of light, which is what you were seeing. By the way, there's kind of an interesting thing. If you take, and that's the reason it has a radiation symbol right here, is if you take a Crookes tube, a cathode ray tube of any sort, or a TV, and you hook it up to too powerful of an energy source. So if you were to hook it up to a very, very powerful battery or to a very powerful generator, it will actually start putting off X-rays, which can cause you to have cancer. And so that was actually the rumor is that watching TV too much caused cancer. Was not true. Uh, but yes, if you were to have hooked up one of these tubes to an outlet that was much, much stronger than the 120 volts that you get in your house, then yes, you could have given people cancer and you could have killed them. And in lab settings, that's actually what's a danger, and that's why all the lab settings always have these stickers on them, because they don't. You could hook it up to something too powerful and produce X-rays. Anyways, how this works is you're going to have a power source. Electrons will go through this wire right here, and that's electricity. When it hits this cathode right here, the electrons are going to leave the cathode. They're going to be attracted to the anode, which right here is your positively charged end. Now, remember, anode attracts anions, negative things. So the electrons are going to be attracted to the anode. One of the ways you can also help yourself remember this is the anode is what you flee from. The electrons flee from the anode, they go away from the anode, and they go towards the cathode. Okay? So you flee from the ants, go to the cats. Okay, now these electrons are passing through this vacuum tube with a zinc sulfide coating. The electrons will go through the slit, so they're a nice narrow beam. Now, if you don't have any charge applied to this tube, they're just going to hit this anode, get reabsorbed, and go back to your power plant or battery or whatever you have this hooked up to. Right here, we have a magnet. And you can literally do this with like a bar magnet too. You don't have to have an electromagnet like they show in the diagram. So if you then bring a negative charge next to this, what's going to happen is it will repel the electrons and they will hit the sides of the tube, causing it to light up. If you bring a positive charge next to this, then it's going to attract the negatively charged electrons and thus again hit the side of the tube. And so right here we see a positively charged side of our bar magnet is causing this electron beam to bend up and hit our tube. And that's just what you're seeing right there. So in 1897, Joseph John Thomson determined the mass to charge ratio of cathode rays and thus discovered the electron, because that's what they were. They were electrons being shot from one end to the other. All right, in 1886, Goldstein observed the positive rays using a perforated cathode. And so he observed positive charges using the perforated cathode to cause the positive charges to collect on one end, like so. Right. In 1909, Robert Millikan used the oil drop experiment. Millikan determined your charge of electron. Notice that before we had mentioned that these were the charge to mass ratio. So if the electron weighed a lot, right, it wouldn't bend much. Much like when you try to curve a car when it's moving, you can't just, tap it and it curves over. You actually have to put a lot of force behind it, right? But if you were to try to move like a soccer ball while it's moving forward, because it weighs a lot less, you can just give it a little bit of tap, right? And so again, the more something weighs, the harder it is to curve, make it move in space. And so when he did this experiment, when Thomson did this experiment, he could only determine your mass to charge ratio. He couldn't determine either the mass nor the charge exactly. He needed one or the other. And so Robert Millikan, quite a few years later, if you look here, about 20 years later, actually figured out the other component and thus we got both the charge and the mass of an electron. And so how he did this was he actually used oil drops to do this. He had an atomizer, which is just a really fine spraying mist that sprayed out oil drops here. And he let these oil drops fall through a very fine mesh that then separated them into very, very fine oil droplets. Now these very small oil droplets, they fell from this end to this end. This right here was a positively charged plate, and this is negatively charged. And so he then exposed it to a source of ionizing radiation, like X-rays. And every time these oil droplets got struck by an ionizing radiation, it caused an electron to be ejected, and thus they gained a charge to them. That charge was equal to an electron's charge. And so he very carefully, finely tuned what the magnetism on these plates was, and saw exactly how much charge it took to suspend those fine oil droplets. Now, those fine oil droplets he knew the mass of, and so he could tell the amount of charge based on the amount that he could put on these plates, and thus suspend the oil droplet. And he finely tuned that, got the charge of it, used that mass to charge ratio, got the mass of it, and that was how we got the mass and charge of an electron. So this is 1895. You may recognize this as an X-ray of somebody. This is using a cathode ray tube. Wilhelm Röntgen, excuse me. And let me give some more. Discovered X-rays by essentially just putting more electricity across this X-ray, this cathode ray tube. 1895, Antoine Becquerel discovered radioactivity. During the following decade and a half, Marie and Pierre Curie worked to isolate pure radioactive substances. And so this is the Curies. They were kind of a neat power couple in science for quite a while. They would publish everything together. They did all their work together. They're kind of a neat story if you ever look them up. Anyways, it's kind of interesting how they originally found radioactivity in the first place. It's because photography was a new thing back then, and people had photography plates because they were playing around with it, using it as, you know, the in thing. It was like drones and that sort of stuff now. Anyways, so one of the people, Becquerel, actually left a rock they picked up on an expedition, and they left that on top of their photography plates, and actually developed the plates, causing a spot to be developed in it. They went, why did that happen? And they found out the rock was giving off radioactivity. And radioactivity literally means that it's giving off like radio waves, or the radio in your car. It's giving off a signal. So if you took a radioactive element and put it next to a radio, like your car has, or the radios that you carry around with you, you'll actually hear hissing and popping in the radio signal, because the radioactive element does give off radiation, radio waves as well. Okay, so when they found radioactive elements, this led into a lot more development in figuring out what atoms are composed of, being able to see inside of an atom. So they took a radioactive source. When I say radioactive sources, really almost all these radioactive sources, even as of today, are pretty much the same thing. You take a radioactive material, it could be uranium, it could be all sorts of radioactive materials, really, whatever you want to use. Each of them gives off different particles, so you'd want to use something that gives off quite a few of these particles. Uranium's pretty good for that. So you take your radioactive material, you put it inside a lead block, and then you drill a hole into it, so you only have one direction the radioactivity is going to go. Because obviously you don't want to be standing where the radioactivity is shooting, right? That would either sterilize you or give you cancer. So, alright, so they took this radioactive source, shot it in a nice beam. Now when they shot it in a nice beam, it made this nice development on a photographic plate. Just a little circle where the beam hit. If they applied a magnetic field across it, though, so they took two positive and a negative plate and crossed where that beam would be shooting, what they found out is it actually made three dots. It developed the plate in three places. And that was what they called a beta, gamma, and alpha decay or particles being shot out. So there was three components here. There was one component that moved towards the positive plate, away from the negative plate, and it moved really far. So if it moves really far, then that means it's very light, right? Think about it this way. If you're trying to curve, bounce back, or let's say we're playing like baseball, and I throw a baseball to you, you hit it, and it goes really far, right? And that's because it's light. So any force you apply, like a magnetic field, is going to make it move a lot because it's light. However, if I throw a bowling ball at you, you're not going to be able to hit it very far, are you? Because it's much, much heavier. And so these alpha particles, yeah, it moved away from the positive plate, meaning it's probably positive, right? It moved towards the negative plate, meaning, again, it's probably positive. But it didn't move very much, which means it has a lot more mass. Beta particles, on the other hand, move towards the positive plate, then that means that they must be negative. The fact that they moved very little means that they must not have almost any mass. They must be very light. And this gamma particle right here that hit the very center, all we really know about that at this point in this experiment would be it has to be neutral, right? So this one's neutral, it's not affected by the magnetic field. And so these are the types of radioactivities they found, the alpha, beta, gamma. And they were able to determine with some of the previous experiments, similar experiments to what we previously just mentioned, that the alpha has a mass of about 4 mass units, atomic mass units. The charge on it would be a +2. The beta type of radioactivity would have a mass that's 1 over 1,837, and its charge would be a -1. And the gamma particle, when they did further experimentation, it was found that essentially doesn't have any mass at all. And it doesn't have any charge either. Okay, so these three types of particles, I'm going to go ahead and jump to the end here and tell you what they are, just so that you have some frame of reference. So the alpha particle was actually a helium nucleus. It has the same mass as a helium, the same charge as a helium nucleus would. It just doesn't have any of the electrons that would normally come with it. Now, the beta particle, this is actually an electron right here. So all the beta particle is, all the beta radiation is, it's just very fast moving electrons. That's it. Now, the gamma radiation, this is actually a frequency of light. So it's very, very high energy electromagnetic radiation, or very, very high energy, same thing as the visible light you see, just much, much higher energy than that. Now, by the way, most of you have probably heard of gamma radiation before. You know, from like the Hulk, Spider-Man, I think, you know, all the superhero movies and stuff. Anyways, yes, that is gamma radiation. No, it does not turn you into a superhero. Hopefully you didn't think that. And yes, it is actually, it's a form of very high energy light. It doesn't just come off of nuclear sources, by the way. It is also hitting our atmosphere every moment of every day. Just, we don't get a whole lot of it down at surface level. So, okay, so in 1911, Ernest Rutherford published in a paper in which he detailed what is called the gold foil experiment. So, using an apparatus that was similar to what we shown right here below, Rutherford actually discovered the atomic nucleus. And so let's go through this experiment to see if you can understand what's going on, and you can use your critical thinking skills to dissect and then possibly apply this in other places. And so he took this radiation source, and this one is just an alpha source. It only shoots off alpha particles. He put gold foil in front of it. And so gold is very dense, and if these particles, if gold is completely filled in, if there's gold all throughout, like we would think if you look at it, right? You look at gold foil and you go, there's no gaps in it. It's completely filled, it's dense, it should block things. Or at least it should have a hole bored in it, right? And so he shot these alpha particles, and what you would expect if this space was filled in is that it would hit the gold foil and all of them would reflect backwards some way. Or maybe go to the side, right? And so likely most of these would hit this photographic plate that he stretched around it right here. Okay, so what he actually found is that almost all of the alpha particles actually just went straight through the gold foil. There was no hole made, nothing. It just went through as if it wasn't there. And then it hit the other side and developed the photographic plate. However, not all of them went straight through. If all of them went straight through, then he would have been like, I don't know what the hell is happening. But what he found is that some of them were just barely deflected. So just small deflections. Some of them were deflected quite a bit, and quite a few of them were actually deflected straight. A few of them were deflected straight back. So the vast majority of them just went straight through, nothing happened. They just hit the other side as if the gold foil wasn't there. The next largest population was just deflected a little bit. And the smallest population of them bounced backwards, as if they'd hit something. And so, what would be a valid explanation for this? Well, a valid explanation would have to include the fact that for most of the space, for most of those alpha particles that are coming out of this alpha source, they're just going straight through, there's nothing there. So it must be mostly empty space. And so the gold foil has to be mostly empty space. It has to be mostly empty. And then, how do you account for these particles then? Well, these slightly deviated particles, that must mean that you have positive charges that are dispersed through there. And these positive charges, whenever you have one of your alpha particles come near it, are going to just slightly deflect it because the alpha particles are also positive, so they'll repel. Now, the final one that comes straight back at you, those ones are going to have to be the ones where it actually hit those positive charges in the gold foil and reflected it back at you, right? And so that means that the fact that very few of them are coming back at you would mean there's actually very, very little space occupied that can actually get hit directly on and then come back at you. That means those positive charges in these gold foil has to occupy a very small amount of space. Okay, so this is actually a graphical representation of what we just talked about. So you guys have probably all heard of the nuclear model of the atom, and this is actually one of the key experiments that supports the nuclear model for the atom. And so right here we have nuclei for the gold atoms. They're surrounded by mostly empty space, which has electrons popping in and out of existence in it. And so these nuclei right here are positively charged. They have positive protons in them. And anytime that you have one of these alpha particles come close to one of these nuclei, it's going to deflect it, and that's that small deviations you saw. Now, most of these alpha particles, because this is almost all empty space, are just going to go straight through it. And that's why most of it just went straight through. And finally, your final case is where it has a direct on collision, and that's going to cause it to bounce directly back. And there you go. That actually shows you the nuclear atom. Okay, so the subatomic particles that make up atoms. These are the proton, neutron, and electron. So here we have the proton symbol. Protons are positively charged, so they have a positive charge, and they have a mass unit of 1. Neutrons have a similar mass, symbol is N, but they will not have any charge. And so protons and neutrons are going to be located in that centrally placed, very small volume nucleus. Notice that these have the vast majority of the mass of your atom. It's 99.99 something percent of the mass of an atom is in the nucleus. Your electrons are going to surround that nucleus. And so your electrons will have a negative charge. These negative charges will be the opposite but equal in magnitude to your protons. The electron, however, will have a mass of 1 over 1,837. So they are an extremely small amount of mass. Now, the outside of the nucleus is where these electrons are typically located. And they sort of they're small enough themselves, they sort of drift and pop around in that outer part outside the nucleus. The atomic number you see on a periodic table of the elements is the number of protons in a nucleus. The mass number that we've been talking about that you also see on a periodic table of the elements is the sum of your protons and neutrons in a nucleus. So isotopes will have the same atomic number but have different mass numbers. That means they have different numbers of neutrons. Right here we see the only case where all the isotopes of an element has its own name. Okay, so these are actually the three isotopes of hydrogen. Now you may have actually heard of some or all of these isotopes before. They are commonly sort of pop up. You can hear about them in the news every now and then. You hear about them in various different stories, and you can also hear about them in like science fiction and stuff as well. So, or if you're interested in space exploration, that's why they want to build a base on the moon, by the way. Anyways, right here, this is protium. This is your ordinary hydrogen. This has a proton and an electron, and that's it. Doesn't have any neutrons. Its mass is 1. All right, right here we have deuterium. Notice pro 1, deut, as in a duo, right? 2. And so it has a mass of 2. It's also sometimes called heavy hydrogen, or heavy waters made of heavy hydrogens, as in a heavy water reactor. Right here, this has a neutron and a proton in its nucleus, and that's what gives it a mass of 2. And again, it only has 1 electron. This right here is tritium, tris and 3, right? And so it has 2 neutrons and a proton for a mass number of 3. And this is actually the radioactive form of hydrogen, and you can use it in various different types of reactors. And that's one of the reasons they want to build like a base on the moon, is they're hoping that they can get some tritium to help them power that, and thus have a power source to keep that base, going. Also, they hope that they can get water so that they can then use the water to fill up things and do other stages of space exploration. So, anyways, right here, this is a nuclear symbol. And so when you represent a nuclear symbol, it will have your elemental symbol right here. And that's going to be things like H for hydrogen, C for carbon, etc. On the superscript in front of it, you will have a mass number. For example, you may have heard of carbon-14 dating. That is mass number 14 carbon. Right here, this will be your atomic number. That's that atomic number on the periodic table. That's also your number of protons. And so when you look at this, this is going to be, for example, like 6 for that carbon. Again, notice that this atomic number and this symbol right here, these really tell you the same information if you have a periodic table. Atomic number is the exact same thing for all of the element. So for carbon, all carbons, it's the same number. And so many people, if you pay attention, will actually drop this number right here. They won't bother putting the atomic number. And that's because if you give them the symbol, hydrogen is 1, helium is 2, you don't need this number because this symbol actually tells you the number. By the way, every time you've heard things like carbon-14, carbon-13, that sort of thing, uranium-235, those are all referring to the mass number, and they're referring to a specific isotope of that element. Okay, so the electron arrangement. This is the Bohr model that explains this electron arrangement. The interesting thing about this electron arrangement is you can actually tell this electron arrangement using the flame test. This is why, if you burn various different elements, they'll give you different colors of flames. And the reason for that is when you burn these elements, you're going to be exciting the electrons in them and causing them to be ejected and taken back up. And when these electrons are taken back up into these elements, you're going to give off a different frequencies of light depending on the electron arrangement of that element. And so, for example, you can tell lithium is lithium because it has a nice deep red flame like so. Sodium has a very distinct yellow color, and it's actually how we like define the meter and everything else. It's because of this very distinct, very specific um, wavelength of yellow light. Anyways, this is potassium. It gives you a nice blue color. Right here, calcium. This gives you an orange color. It's actually quite pretty. And strontium does something kind of interesting. It gives you a white color in the middle flame, and then it does sort of a reddish color around it. Okay, so a continuous spectrum. I've actually shown you what would be referred to as a line spectrum, meaning it has a very specific frequencies that it gives off, versus what is a continuous spectrum, which is when light is emitted from a solid substance, passes through a prism, it produces what is called a continuous spectrum of colors, and that is the entire rainbow worth of colors, right? All the different colors. Okay, so as opposed to a continuous spectrum that would be all the different colors, there's line spectrum. So line spectra is when light from a gaseous substance passes through a prism, it produces a line spectrum, meaning it only produces specific frequencies of light. It doesn't produce the whole range. So you see here this CD only produces 1, 2, 3, 4, 5 lines right there. Each of them has their distinct wavelengths. And when I'm saying wavelengths, that actually means the colors. Okay? The colors are specific wavelengths. Right here we see the continuous spectrum that has all the different frequencies. By the way, if you're wondering what's going on over here and over here, these don't have colors because we can't see them with our eyes. So this right here is infrared. It's below red, and this up here is actually UV, and so it's above violet. And that's why it's you can't tell the difference between these other colors right here because you just can't see it. Anyways, um, notice by the way, if you took the color wheel, the continuous spectrum is just the color wheel folded. If you're ever curious, that's actually why the color wheel is the color wheel and exists as is. It's because of this continuous spectrum and the frequencies that each of these colors are. So, while I'm on it, there's a sort of interesting side note that you might want to know at this point about light, and that is that black actually is the color of your eyes giving up and saying, I just can't see these enough of this color to actually tell you what it is. So I give up, it's black. And white is actually you seeing so many colors and so much of it that your eyes go, okay, there's just too much for me to communicate to you. It's white, okay? That's it. And then gray, of course, and brown is actually brown is if you have a little bit of extra red, but you have so many different colors you can't tell the difference. And so your eyes go, brown. It's sort of reddish, I guess. And then gray is where you have, a moderate intensity of light, not too low, not too bright, and you have so many different colors that your eyes just go, I give up. I don't know. Okay, so a quantum. You may have heard of quantum chemistry before. Um, you may have heard it's difficult and oh my goodness, this is terrible. It's actually not as bad as you probably think. Now, quantum is a tiny unit of energy produced or absorbed when an electron makes a transition from one energy level to another. It's why you're giving off these different colors of light. For example, right here we have different energy levels. You can think of them like floors of buildings. So on the first floor, it's the lowest energy. If you try to fall from the first floor, it's not going to hurt. The second floor is higher energy, or the second energy level is higher energy. It's like the second floor. If you fall from the second floor to the first floor, it might hurt a little bit, right? And that's because you have more energy up here in the second floor than you do on the first floor. What happens if you try to stand halfway in between the first and second floors? You fall down to the first floor, don't you? Much like in a quantum situation where you have your electrons. If you try to raise an electron from right here, it's just going to fall right back into the first floor, first energy level. If you were to shoot it up to here, it would fall back to the second energy level right here. Okay, so what creates those different wavelengths of light that are coming out, those different colors that are coming out? Well, what it is if you boost electrons up to higher energy levels and then they fall back down, when they fall back down, they're going to give off that color of light. So for example, right here we have violet. Violet is a higher energy form of visible light. And so the violet light is given off when we have an electron that falls down from our fifth to our second energy level, from our fifth floor to our second floor. That has quite a bit of energy, and so we get this fairly high energy visible light. Now, this green color has less energy to it. It's a lower energy form of visible light. And so that's from when you have an electron that falls from our fourth to our second energy level. And then red is the lowest energy of these three visible lights, the lowest energy visible light. And so that's when you fall from our third level to our second level. You only fall down one level, but it's a pretty big fall. It's a pretty big difference in levels. Okay, these right here are infrared light wavelengths. Infrared wavelengths are even lower energy than visible light. And so these are just small falls from like your fifth to your third energy level. You can see that's fairly low, small difference. Okay, so quantum is a tiny unit of energy produced or absorbed when an electron makes a transition from one energy level to another. Quantum literally means a quanta, or a specific division or steps of energy. So when electrons are in the lowest energy state, they're going to be said to be in the ground state. And you can think of that like the ground floor, right? It's the lowest energy. If you fall off the ground floor, you don't get hurt. When energy from a flame or other source is absorbed by the electrons, they will be promoted to a higher energy state. You can use electricity, heat. There's a variety of different ways you can boost electrons into this higher energy state. By the way, that's how like neon signs work, is they use electricity to boost those electrons into a higher energy state. This higher energy state is said to be an excited state, and that's what that's called. It's excited. And so if it goes then from the excited state down back to the ground state, it's going to release light, which is actually, again, how a neon sign works. So when an electron is in an excited state, returns to the lower energy state, it emits a particle of light, or a quanta of light. These quanta of light are called photons. And so it emits a photon of energy. If it is the visible form of light, if it's the correct energy for your eyes to see, then it's going to be observed as light. If it is not a visible form of light, you of course won't be able to directly observe it, but it can be detected. And so it may be, if it's very low energy, something like infrared. If it's very high energy, it might be UV or X-ray. Okay? Now, if you're curious, humans can see a very, very narrow band of light. But there's actually quite a few organisms on the planet that can see quite a bit more of the spectrum of electromagnetic radiation, which we typically like to think of as light. And so, for example, there is actually a type of shrimp that lives on the ocean floor that can see well into the UV and all the way down almost to the microwave, like microwave radiation that you use in your microwave at your home or that you use. That's the same thing as Wi Fi, by the way. It could see Wi Fi signals. Can you imagine? All right, so energy states or levels, these are sometimes called shells. So these energy states that we mentioned before, these are sometimes called shells. And that would be that first energy level, it was on the bottom, second energy level, third energy level that we saw in the previous figure. Right here we see the elements that have different shells and where they have their electrons. So hydrogen has an electron that's in the first shell. If we were to add energy to it, it could go into the second shell and become excited. It would then drop back into the first shell when it's going back to its ground state. And right here we see helium, it has 2 electrons in the first shell. Lithium has 2 electrons in the first shell and 1 electron in the second shell, and so on. Now the quantum model of the atom is a probability-based model. It is composed of principal energy levels, sublevels, and orbitals. So the principal energy levels, these are the shells, these are the energy levels I mentioned before. These are roughly going to correlate to your distance that an electron is from your atom's nucleus. So again, it's best if you think of your atoms as little tiny Earths, okay? And each of the energy levels would be like the levels in a building. So the first level, the first principal energy level, the first shell, would be the closest one to the ground. The second level would then be the next one up. It'd be further away from the nucleus, much like the second level of building is further away from Earth, right? And then the third would be further away, and so on. Now notice that each time we get higher, we actually have more volume there. We have more space. And each time that we get higher, it's going to be higher and higher energies. Now the next one is the sublevels. These can be referred to as subshells. That's actually the better terminology. And the way I want you to think of subshells is our energy levels, those are our floors of a building, right? Our subshells would be like the rooms in those floors. So they're each going to have different shapes, and they'll divide up that shell or energy level into different spaces or shapes. And so again, they're like the rooms in a building. And so finally, there would be our orbitals. The orbitals are going to be regions in space that represent a high probability of locating an electron. It's where you're 90% likely to find your electrons, okay? So each of your sublevels is going to have one or more orbitals. These are your desks in your building. So again, it's like the lecture halls, right? We have our floors, which are our energy levels, or our shells. We have our sublevels or subshells, which are the rooms. Inside of the rooms, there's desks. And those desks are our orbitals. Now, each desk can hold 2 people. Each orbital can hold 2 electrons. Remember, though, when you sit down at a desk, do both people sit down in the same chair? No, that's silly, right? So each person is going to sit down in a different chair. One in the upper chair, one in the lower chair, right? And when we have electrons in orbitals, they have to be in different energy levels or different energy states or different places in those orbitals. And so those are represented by an upper spin and a downward spin. So right here, these are different types of orbitals. These are depicted based on their sublevels or subshells. So the shapes of these are depicting the subshell. So an S subshell looks like a sphere. You see that? Notice that a sphere only has one direction it can be facing. If you rotate a sphere, it's still the same sphere, isn't it? And so there's only one orbital in your S subshell. It only has one shape. It's like a very, very tiny room, okay? That can only have one desk in it. Your p orbital, on the other hand, it looks a bit like a dumbbell. See that? And this is just showing you the probability of finding electrons. Now, this p orbital, you may notice that this is in the x direction right here, isn't it? So you could have had one in the y and one in the z, up, down, coming towards you as well. So that's what we see right here. This is your S subshell. These are 3 different P subshells in different directions, X, Y, and Z. And so what you see here is the P subshells can actually have 3 orbitals in them. So it's like a room that can have 3 desks in different directions, in different places. Altogether, they're going to take up most of the space that you would have in something like your second energy level. And so they take up pretty much all this space, and you can see they all have sort of distinct areas that the electrons will be able to occupy. Alright, so this is an electron configuration. This allows us to represent the arrangement of the electrons in an atom. And so what we do is it's an address for our electrons. So we're on the first floor, we have the S room, and there's 2 electrons in that desk. And so it is a 1s2, representing that we're on the first energy level, where we have the S sublevel or subshell, and there are 2 electrons in those orbitals, in those desks, in that desk. This right here would then be a little bit more complicated electron arrangement, or electron configuration would be the correct way of saying that. This one's for nitrogen. And so nitrogen, okay, I'm going to need to fix these notes. I'm going to release this part of the video first, and then I need to rearrange my notes here. Okay, you take care.